Physics. Going to do from chapter 2, numbers 2 through, oh geez, was it six? I think 16 evens. I don't think 18 looks like it's in the next section. I think that's right. All right, number 2. Let's get on it. Compute your average velocity in the following two cases. We have case number 1. You walk 73.2 meters at a speed of 1.2. meters per second. And then run 73.2 more meters at 3.05 meters per second. All right. So let's see. We've got, we want to find what? Our average velocity. So average velocity is your displacement divided by your time. So I think the thing we're missing here is our times. So since velocity is equal to, I have it right here, don't I? So time, if I moved time up here and velocity down here, time is equal to displacement over that constant velocity. So I think I can find times for each of these. So let's see, 73.2 divided by 1.22 is, this takes 60 seconds. And then here, 73.2 divided by 3.05 is 24 seconds. So here, that means my average velocity is the distance that I covered. This is just on a straight track in one direction, not turning around, so it's going to be 146.4 meters in a total of 84 seconds. So it looks like I'm getting 1.74 meters per second for that. In part B, you walk for 1 minute. 1 minute. Okay, so I think I have the times there. So this is, I think the setup for this is much easier. Oh no, just kidding, because 1 minute, I still need to find the distances now. Sorry, so I need to do the, now we have 60 seconds, and for the first leg we're going to do the 1.22 meters per second, and then we're going to do another minute doing the 3.05 meters per second. All right, so let's see what we have here. We need to figure out how far, so we can get my total distance here. So 60 times 1.22 is, hey, that's the 73.2. And 60 times 3.05 is 183, so that's different. Okay, so my displacement is the sum of those two, which is going to be 256.2. Got that right, and then that's 120 seconds. That gives me about 2.14 meters per second. And they want a little graph of both. And we'll just talk about that slope. So let's see, position, time, In both of them, the first distance was 73.2, so I think I'll just mark that off, 73.2. And then in this one, it did 73.2 again to get up to 146.4. And then this one went up another bunch. So 256, that's like up here, right? So somewhere up there. And then for times, what do I have? 60 seconds. There's another 60 seconds. Oops. 60 seconds. And then in this one, I went 60 seconds and then 24 seconds. So that's somewhere like 84, be somewhere around there. And then 120 is there. Okay, so in scenario 1, I got to 73.2 in 60 seconds. And I think that same thing happened here. Right, that was the same both times. And then on this one, I got to the second 73.2 in 84, or 24 more seconds. So that's steeper. And then the second one took more time. I got out to here. I don't know. I'm just sketching this graph, so I don't think that those are collinear. I don't think they're along the same. Oh, they are. They are because the slope is the same, but we did it for longer, so we got out to a further point. So that's all good, right? So the things that we found here and here, this is the slope of that. Connect the origin to this point. All right, that was like the total slope there. 146 divided by 84, right? That'd be the slope of that. And then this right here was from the origin all the way out to here. Sorry, that is a funny looking straight line, which was 256, that total here divided by the whole 120 seconds. All right. Number 4. A car travels uphill at a constant speed of 40 kilometers per hour and returns down the hill at a constant speed of 60 kilometers per hour. Calculate the average speed for the round trip. Not average velocity, that would be 0. We're back at the start. So it travels up a hill. It doesn't tell us how long the hill is, so I guess that doesn't matter. So we're going to go up the hill a distance d, and then down the hill also a distance d. It is... Let's see, we're going at 40 kilometers per hour, and going at 60 kilometers per hour here, right? And we want to know the average speed, so that's V average is the total distance for, this is average, I should say, speed here. My average speed is the total distance. I can't put delta x here. I shouldn't put delta x here because delta x would actually be 0 since we're back at the bottom of the hill. So this is the total distance over the total time. So we need some kind of expression to relate these things. The distances are the same. The times are different. So time, this is going to be longer than this time, right? Because we went slower here. So let's see. What's time equal to? We have, if we rearrange our little equation, I know that time is equal to that distance divided by the velocity. So time 1, let's see. I think I need to actually solve for the distances, don't I? So the distances, because those are the same, I can set them equal to each other, and that's good. Yes, so this distance here, distance is equal to velocity times time. So this distance is 40 t1, and this distance is equal to 60 is t2. Let's try it this way. We'll see what happens. So my average speed I'm not liking the way this is. Okay, let's do both. Let's try the, so if I did it the way I was setting out to at the beginning, where I have delta x, which is d over v, I think this is going to be better. Yeah, this is the way. So look, the moral of this story is not that your confidence in your physics teacher should be rattled. That's no good. We don't want that. The moral of the story is it's not always 100% obvious, even if you're a seasoned physics teacher such as myself, what the first correct move should be. Sometimes you just have to push things around a little bit and try stuff until you can find something that works. I like the metaphor of, like, here's like the problem, and you're sort of like walking around the problem and like circumspecting it and seeing, is this a good way in? No, that's not going to work. What about this? Could I get in from here? Oh, maybe I'll try that. Oh, that didn't quite work. So, you just have to try different things. And definitely, you should not feel like, oh, if I don't know what to do right away, that means I'm bad at physics. That is just not true. People who are really good at science are people who are willing to keep banging their head against a problem until some path forward reveals itself to them. All like the important, new, interesting, good work that scientists are doing, they're trying to solve problems that people haven't solved before. We don't know the answers. So the path forward is never clear. So anyway, that concludes the inspirational speech part of today's video. So anyway, if you're wondering, like, how did I know? Like, what was I thinking about? What was the McGrath thought process here as I went through these and I was like, oh, I don't like this. Well, this is what I was thinking about. When I set up this average speed, I'm going to set up this total distance, right, which is 2d over total time, and then so my time is t1 plus t2. Well, I've got the total distance here. I've got those d's here, but so like this d and this d, I could say that this is 40 t1 plus 60 t2, but that's not gonna, there's not really any algebra I can quite do here to resolve that. So that isn't going to really work. On the other hand, if I do it this way, then my total distance is 2d, and then here I have the times in terms of the same d. So this is going to work. I think we did something like this in the homework, the odds from this section also. So that'll work. All the d's cancel out. So I get 2 divided by the sum of those two fractions. That should do it for us. So 2 over upside down of 40 plus upside down of 60. And if you just looked at that problem and you're like, oh, that's easy, it's 50, because that's the average of 40 and 60, then shame on you. You shouldn't have done that. Not after yesterday's homework. All right. Good talk. 1992 speed record for a bicycle was set by Chris Huber. His time through the measured 200-meter stretch was a sizzling 6.509 seconds. And then some other guy beat Huber's record by 19 kilometers per hour. What was the time? Okay, so this is just a little bit of dimensional analysis, basically, or unit conversion. So let's see. The first guy went 200 meters in 6.509 seconds. So I think I need to turn this into, actually, let's not even do that yet. I need to turn this into kilometers per hour. So 1,000 meters is 1 kilometer. And 3,600 seconds is 1 hour. So before I even bother doing that, let's just do the whole thing. I have 200 divided by 6.509 divided by 1,000 multiplied by 3,600. So that was, let's see, what did they give me for significant digits? They gave 19.0 kilometers per hour, so I'm going to also round this to the nearest tenth of a kilometer per hour. Okay, so the other dude went 19 kilometers an hour faster. Wow, that's like shattering that record. So that would be, let's call him the new guy, Sam. The new guy beat this by 19, so he went 129.6 kilometers per hour. And now their question is, what was his time through the 200 meters? Well, I think I'd like to convert this back to meters per second, wouldn't I? So just do this process backwards or the other way. And 129.6 divided by 3,600 multiplied by 1,000. Really? And that's 36 meters per second. And then we would like to know what was his time. So if we're just using this, velocity is equal to, this is our average velocity, displacement over time, then his time would be equal to his displacement, which is 200 meters, over his velocity, which is 36. So 200, not 2,000, divided by 36 is 5.556 seconds. All right, that's fast for riding a bike. That answer is a tiny bit different than the one in the book. Oh, you don't have the answers in the back of the book, so I don't even have to tell you that. I can just pretend that that's exactly the right answer. They just rounded differently along the way, and they have a 4 here instead of a 6. So we'll keep that. All right, the panic escape. This is a little scary. So if pandemic isn't enough for you, make you feel unsettled, here's the panic escape. So you got a person, I'm going to make my people just look like blocks like this. A person is 0.25 meters deep, and this distance L is 1.75 meters. And all the people are spaced out the same amount, 1.75 meters, and so on. So the question is, if all these people are like trying to get out of that door and it turns out that it's locked, then there's going to be like a buildup of like a layer of people there. And they want to know at what average rate does the layer of people at the door increase? Okay, well, they're going, all the people are moving forward at 3.5 meters per second. And notice that 1.75 meters is exactly half of this, right? So if you're going 3.5 meters in 1 second, then you can do the math if you want, but it's going to take you half a second to go that distance, right? So that means 1/2 second later, so this is like at time 0. Sorry, my door, I wanted that to be in the same place here. So half a second later, you're going to have person number 1 is going to be up against the door, and then the spacing here would be the same because they just got to the door in that half second. So the second person now is here, and they're still spaced by 1.75 because this person just got there. So the gap between them, since they were going the same speed, that didn't increase or decrease. Okay, so there's that. And that's actually enough to answer this question. You could do like one more if you wanted to. I'll just do that real quick. So then at time 1 second, that's enough time for this person to traverse that distance. So now you have this person, another person, and then this person out here. Well, this person just got to this location, so that spacing is still the same because this person and this one were going the same speed toward the door, and this one just got here, so that distance has not increased or decreased. Okay, so right now we have a layer of people here that's 0 meters deep. Here it's 0.25 meters deep, one person. Here it's half a meter deep, and so on. So it took half a meter, or it took 1 second for it to increase to half a meter. So there's your answer for part A. It's at half a meter per second is the rate that the pile of people is increasing at. And then B, how long does it take for the pile of people to be 5 meters deep? It will take, well, let's see, to get to 5 meters, that would be 10 seconds, right? You need 10 of these. So you could set that up in equation form if you want, where you say you can use any one of the forms of this. Let's write it like this time. Average velocity or constant velocity times time. So they want to know 5 meters. I know what this is. How long will it take the time? So you divide that there, and you get the time as 10 seconds. All right, that's how you do that. To number 10, to set a speed record in a race car, it's got to be driven first in one direction in time t1, and then the opposite direction in time t2. To eliminate the effects of the wind and obtain the car's speed vc in a windless situation, should we find the average of d over t1 and d over t2, or should we divide d by the average of t1 and t2? So the car is going to go this way, and then the car is going to go this way, and let's say the wind is blowing this way. So we are supposed to assume that the wind is going to help out the car, so that when the car is going this way, its velocity really will be velocity of car plus velocity of wind, and here it'll be velocity of car minus some hindrance from the wind, same amount but the other way. Okay, so the distance is the same, but the times will be different. So how do we figure out what is the correct average velocity? Well, that's going to be the total, that total distance, and I should say really we want speed here. Again, sorry about that, because this is, the delta x would be 0 if you go this way and then you go back again. So really we want here the total distance. I think it's worth emphasizing that, over the total time. Right? Okay, so let's see what we can do here. The what is the total distance? That is going to be 2d, right? And then what is my total time? The time here is going to be, remember that time is equal to that distance divided by velocity. So here, this time is going to be the distance d over vc plus vw, and here it's going to be d over VC minus VW. And if we find that total time and add those together, that's D there we go. Okay, so what does that mean? Well, the D's are going to cancel out here. And let's just do a little algebra here. So the D's cancel out, and I get 2 over 1 over VC plus VW plus 1 over VC minus VW. So now we just need to figure out what we are looking at here, and I think that if, let's see, how about if I multiply top and bottom of this by 1/2? I hope this is going to be a good way to go here. I'm feeling a little iffy about it, I've got to tell you. Like I'm going to have to backtrack a little bit, kind of like what happened on number 4? Because this is looking pretty messy. So let's see that the question is divide D by the average of T1 and T2. I think that we need to check those two methods and see which one is going to be equivalent to some version of what we have here. Let's try that and see if that works. So to eliminate the effects, should we average D over T1 and D over T2? Well, let's try that. So D, this is method 1. I'm just going to like write out what they're saying. Method 1, they're saying should you average D over T1, which is this, and D over, oh, this is looking good. They want us to, so they're asking, is method 1 take D over T1, D over T2, and average them. So when you average things, that's the same as adding them together and dividing by 2. And I think that that is the same as this, isn't it? Boy, I'm sure hoping that it is. Yeah, I think that it is because, let's see, if we multiply by, I want to be able to convince you that this is good without doing too much algebra. Well, I guess I just need to do the algebra, huh? Okay, so much like in calculus, we need to simplify these things so we don't have so much of a mess here. So this here, I have a D on the top, D on the top. That's the same as 1 over VC plus VW, sorry, plus 1 over VC minus VW. And that is equal to, and then we have that all over 2, and then those flip over, divided by a fraction, same as multiplying by its reciprocal, so I get 2 VC over 2, which is VC. Oh, you know what? I didn't need to do all this. Sorry. Because by taking this method 1 and using our times here, what I just showed is that if you do this, if you set it up like distance divided by the first time plus distance divided by the second time and then average those two, what I just showed is that that's equivalent to VC, which is the velocity of the car without the wind. So that was all a distraction. Sorry about that. Is that part A? Yeah, so method 1 is the correct one. What is the fractional difference in the two methods when a steady wind blows along the car's route, and the ratio of the wind speed VW to the car's speed VC is 0.0240? There's a couple ways you could do this. You could actually just pick a velocity for the car, some big number, and then use that and pick a distance also. That might make it kind of easier to work with. I'm going to do it just with an abstract and not do that, but it would totally be a reasonable option to say, let's say it's going like 1,000 meters per second or something. That's probably absurdly fast, but it would be an easy number to deal with. So what I'm going to do is, if that's the ratio, if VW is 0.0240 of VC, that means that VC plus VW is equal to 1.024 VC, and VC minus VW is going to be equal to 0.976 VC. So it's that little plus or minus of the wind. Okay? So they want to know what is the fractional difference in the two methods when a steady wind blows. So the right way to do it is this. Right? So if I need to pick some distance d, and they want to know the fractional difference in between the VCs. Okay, so I don't actually have to do this method because I know this method gives the right answer. So this method is the correct one. Method 1 is just going to give me VC. So the question is, what does the other method give? So method 2 is, let's see, we didn't ever tested that one because we determined that method 1 was right. So that one is divide d by the average of the times. Okay, so method 2 is take d and then divide by the average of the times. So here are the times. That's d over VC plus VW. Plus the other time minus VW. So that's the distance divided by the average of the times. Okay, so I need to kind of clean this up and turn this into some multiple of VC so I can compare them. So let's see here. The D's cancel out, and I'm going to take this dividing by the 2 down here. If I multiply top and bottom by 2, I can move that 2 up to the top. And then I have 1 over, now this VC plus VW, that's this. So that's 1.024 VC plus, and then likewise this is 0.976 VC. So let's see what I need to do here. I guess I need to, let's see, if I multiply the top and the bottom of this by VC. Then I have 2 VC over, and then I'm adding these two things. I've removed these denominators and moved the VC up to there. So I just have 1.024 to the negative 1 plus 0.976, the negative 1. All right, there we go. Now we're cooking. And let's see. That gives us 2 over 1.024 to the negative 1 plus 0.976 to the negative 1. And that is 0.9994 VC. So what does that mean? If you use method 1, you're going to get the correct speed. If you use method 2, you're going to get something that's a little bit smaller than the correct speed. Right? All right. If you're thinking like 8 and 10, 8 wasn't so bad. 10, if you're thinking to yourself, geez, this is crazy. This is good practice. You have to kind of go out of your way, and our book authors, they most certainly did. You have to go out of your way to make difficult constant velocity problems. And, this is just to get some experience using this velocity is equal to displacement over time. When is this true? This is true if you're talking about average velocity or if you're talking about something that's going at a constant velocity. Now, when we come test time, this is going to be, we're not going to be interested in questions of this difficulty level with just constant velocity. So if it's stressing you out, the difficulty of these problems, they're kind of like weirdly difficult. So I hope that makes you feel a little bit better, maybe. So speaking of problems that are weirdly difficult, here's a good one. This is a fun problem about the traffic shockwave. I think part A is pretty easy, and part B is a little tricky. So let's get into it here. If you want to, if you're like, you know what, I've had enough of these hard problems and I tried 12 and it's like too much. This is kind of like a trickier version of the panic escape problem. If you're fed up with this, you can skip this one. I think you could skip. This is a little 3-dot problem. Our book puts 3 dots next to problems when they think that they're hard. That 13 that we did yesterday, that wasn't that hard. So, hang in there if you want and skip it if that makes you happier. Okay, so let me, in the interest of time, I made a little diagram ahead of time for this one. So, oh, that's like a diagram for, that's the wrong part. That's kind of for part B. Let me do part A here. So, part A is the cars, which are basically like a car plus a buffer zone, which is 12 meters long, are separated by some distance that we don't know, and then like car plus buffer zone, they're all stacked up here, and then at some point they release themselves from the congestion, but we don't really care about what's happening at that end. So the first question is, what would this distance D have to be for the traffic shockwave to like stay in place? In other words, it takes the same amount of time for this car to get to here. Let's say this is car 1, and this is car 2, this is car 3, and so on. Then if the traffic shockwave is going to stay in place, then this car, which is going at 25 meters per second, and these cars, which are all going at 5 meters per second, that's weird looking. There we go. So that would mean that car 1 would end up exactly in this spot in the same amount of time that it would take car 2 to get to right here. So if that happens just right, if car 1 kind of replaces car 2 just as car 2 gets to here, then, well, then the traffic shockwave stays in place. And so that would mean that for car 1 to get from here to here would have to take the same amount of time as car 2 getting from here to here, right? Well, what are those distances? How far did car 2 go? Car 2 went exactly 1 car plus buffer length. It got to right here. So car 2, the distance it traveled, it's delta x, if we want to stick with that. Kind of symbology, notation. The delta x is 12 meters. And the time is, well, whatever the time is, and the velocity of that car 2 is 5 meters per second because it's in the slow group. Okay, car 1, if it's going to get from here to here, then the front of the car needs to get from here to here. And that's not just a distance of d, it really has to go d plus 12, because we need it to get from here. If it goes a distance d, then it's going to be like here, right? Because the front of the car, whatever part of the car you pick to be your reference point, that's the part of the car you got to stick with. So if the front of the car goes a distance d, then the front of the car would be here, but we want the front of the car to be here. So the distance this one is going is really whatever this d is that we're looking for, plus 12. It takes some amount of time, but it's the same amount of time as car 2 getting from here to here, if we want this to work just so. All right, and then if I want to solve for time here, I know that time is equal to the displacement divided by the velocity, and I'm setting it up that way because I know the times are equal to each other, so I think I can get an equation out of this. So for car 1, I have time is equal to d plus 12 over 25. That's the delta x for this. And the times are equal, so that's got to be equal to the same time for this car, which is 12 meters over 5 meters per second. And that's it. So it looks like, do a little bit of math, looks like d is 48 meters. All right, that's part A. And then part B, they said, well, what if the distance is 4 times that? So in other words, what if the distance, or sorry, twice that, I guess they said. Is that what they said? Yes. So what if the separation is 96 meters? So here's what I did to set this up. I said, if you're wondering, wait a minute, they said 96. Well, this distance right here from here to here would be 96, but the 108, that's 96 meters plus the car plus buffer length. Because what I want is I want to know what this distance right here is. That's 108. Right? So now we know what this distance is, and we want to figure out what's happening to the traffic shockwave. Okay, so the first thing that I figured out in my picture here, this is car 1, this is car 2, and now this is car 1, and this is car 2. I just thought about this for a minute. Now, you probably don't like it when your teacher says, just think about it for a minute, but I thought about this for a minute, and I thought, if this distance is greater, then the cars, they're still going at the same speeds, then the whole shockwave is going to have more time to move up. So I was very confident at the beginning of this, drawing my picture, that for sure, like where the shockwave is, it's going to be moving forward. Like it's going to have moved more forward by the time this car catches up to the back of it. So that's why I have my car 1 here instead of like in the last part. All right, so then I just set up some different distances. So I don't know how far that D, like the difference between where car 1 would have been like in part A and how far it has moved forward. I don't know what that distance is, so I called that D. And then I called this distance, these are my little buffer zones, right? I called this distance where car 2 is, from here to here, back of car 2 to back of car 2. That's this distance D, which I just made up a name for, plus a whole car plus buffer. And I want that distance because that's how far car 2 traveled. So here's a similar little table to what I did in part 1. Again, it's going to take them the same amount of time. So for car 1 is traveling that 108 meters plus D to get to here. And car 2 is at 25 meters per second. And car 2 is traveling D plus 12, back of car from there to there. That's D plus 12 at 5 meters per second. And then I did exactly the same thing that I did in part A. I found these expressions for time and set them equal to each other. Did a little algebra. And I found that D right there is 12 meters. Okay, but that wasn't the question. The question was, how fast is the shockwave moving? Well, here's the back of the shockwave here, and here's the back of the shockwave now. So if you're like watching this from a distance and sort of watching the shockwave migrate up the highway, then you're interested in this back of shockwave got to here in how much time did that take. So we are moving, let's see, we've got the time of that. If we wanted to figure out like how long that took, the amount of time, you could use either car to figure this out. But here I figured out, okay, the amount of time that this happened in that time, this car 2 went from here to here, which is D plus 12, or 24 meters, since we now know what D is. And that happened it happened at 5 meters per second. So I did the same little equation that I set up here, this right here, to figure out that took 4.8 seconds. Okay, now we want to know how fast it's moving, so what distance was covered here? Well, the shockwave, the back of the shockwave went from here to here, a distance D of 12 meters in 4.8 seconds. 12 meters in 4.8 seconds. So that is 2.5 meters per second. So the back of the shockwave is sort of migrating up the highway at 2.5 meters per second. A little bit more thinking about that would mean that if the separation between the cars in the last part, this distance turned out to be 48 meters. So if that distance was less than 48, then the shockwave would be moving this way. It would be backing up through traffic this way. If the separation is exactly 48, then for these particular conditions, that's where it looks like the shockwave is in place, and then anything bigger than 48 meters, it's going to migrate forward. If you've ever spent a lot of time on highways with congested traffic, like up around DC, I did a lot of driving up around Boston back in the day. This is a thing. You can see these shockwaves, and you can kind of feel them moving forward or backward. All right, so on to a couple easy little calculus type problems. All right, an electron moving along the x-axis has position given by x is equal to 16t e to the negative t, where t is in seconds. How far is the electron from the origin when it momentarily stops? Well, how are we supposed to do that? This is physics, so calculator's always allowed. So I'm going to make a graph of this position versus time. Of course, my calculator wants to make those x's, so that's okay. E to the negative x. And let's see, how should I scale it? Well, before I go hitting graph, the x-axis is time, so 0 to, I don't know, we could go to 10 seconds, we could try that. And then the minimum positions, 0 to 60, that could possibly work. I'll give that a shot. Okay, so it looks like maybe we should go 0 to 5 and 0 to 10. Let's try that again. So see how that looks. Oh, it looks good. Okay, so what are we looking at here? This is a graph of position versus time, and it looks kind of like this. So how would we look at this graph? What would we be looking at if something turned around? They want to know, the question is, how far is the electron from the origin when it momentarily stops? Momentarily stops means velocity of 0, that's the turnaround. Well, velocity is the slope of this, and if you're thinking about tangent lines, that would be where the slope is 0. Or if you're just thinking about, look, this is position, so if it's going forward and then backwards, right, it's going into more like lower positions as it drops down here, then this must be the turnaround point. So what I need to find here is this maximum. So second calc, you've done this before, maximum, and then you have to do the little left bound, right bound game. Did you know that you don't have to move the cursor around? You can actually type in your left bound and right bound. I set my window from 0 to 5, and my maximum right there is definitely in between 0 and 5. So I'm just going to type those in. 0, 5. I hate playing that game with the cursor. It makes me crazy. So it looks like there's a maximum at time 1. That's the x-coordinate is time. The position is 5.886 meters. And that is what they're asking for. Right? Cool. Last one. The position function x of t of a particle moving along an x-axis is 4 minus 6t squared. At what time and where does the particle momentarily stop? Okay, I could make a graph of this, but I'm going to try to do a little bit of calculus here because I can. So the derivative of this is dx dt. That is velocity. So if I take the derivative of this, derivative of that is 0, and then that's minus 12t. If you're like, oh, wait, I think I get it now, then pause the video. Try this yourself. So at what time and where does the particle momentarily stop? So for it to momentarily stop, that would have to be where the velocity is 0, right? So where is the velocity 0? Well, that only happens when, if you want this to be 0, then t's got to be 0. So at t equals 0 is the only place where that happens. And where does that happen? So at time 0, if you plug 0 into this, then the position is 4 meters. At what negative time and positive time does the particle pass through the origin? Okay, so passing through the origin is having a position of 0. The origin of a number line is just, we think about the origin as on an xy plane, but if you have just a number line like this, and so on, this is the origin. It's just a one-dimensional origin. So that means, where is it? The origin is at x equals 0. So when does that happen? Well, we just solve for this. So I guess t is equal to plus or minus the square root of 2/3 seconds. Whatever that is as a decimal. about 0.82 seconds. D,